So good morning, welcome to my classroom. We continue the discussions from where we left last time. You recall that we were looking at this equation, y derivative equal to f of xy, xy belonging to an open we assume D is open, connected, etc., etc. Now, suppose x naught, y naught is a point D. Then what we have proved is this, that if we demand y at x naught to be y naught, or we look forward to a solution of the equation satisfying the initial condition here, then you see that there exists some h positive such that on mod x minus x naught less than or equal to h, there exists a unique solution. Hi, good morning, yeah. Just okay, let me, yeah, tell me. Oh, you want me to mute this? Yeah, okay, I'll do that. It's okay? Right. Yeah, so there exists a unique solution of this initial value problem. So the initial value problem consists of this. So there is some interval on which this is true. As I said, it is a local existence uniqueness theorem that we have proved. Now we want to see, we have seen that with an example that the uniqueness is guaranteed only under certain conditions, like the Lipschitz condition. Okay, now what we want to do is, suppose we knock out that condition, then what do you get? Do you still get the existence of the solution? Now this is going to be the theme in the first lecture that I do today. So in this context, okay, I'll just give the broad strategy. The broad strategy is this. See, you have this differential equation. I'm taking a rectangle R as we defined earlier. Now, what we do is, see, we are assuming F to be continuous on R. And R is compact, therefore it is bounded there also. So F is bounded by some M or something like that. It is immaterial. Now, what I do is, see, it's a rectangle on which suppose x naught, y naught is a point. You are going to use that as an initial data. This is your R on which it is bounded, and what you can do is that f can be approximated by a polynomial. See, given epsilon, there exists a polynomial p epsilon x y such that mod p epsilon x y less than. So what you do is you approximate the function by a polynomial. The next step is, instead of considering this equation, we consider this equation. With the same initial data, Okay, do a very natural thing. You see, the advantage of working with polynomials is that they are nice functions, and you see that you can immediately prove that all polynomials on this interval, on this region, satisfy Lipschitz condition, and it is uniformly Lipschitz. So P epsilon is Lipschitz. Therefore, this differential equation has both P epsilon is continuous, P epsilon is Lipschitz. Therefore, you can apply the existence and uniqueness theorem. So there exists a solution y epsilon on some interval on mod x minus x naught less than or equal to h. This is possible. Now we will do the details soon. Now what one does is this, look at these class of functions. What you can prove is that this function is totally this set of functions. So now you choose a sequence of functions. Take epsilon n going to 0, a sequence epsilon n such that epsilon n goes to 0. Then you see that corresponding to each epsilon n there is a yn. So it gives you a sequence of functions ynx, each satisfying the corresponding differential equation. Now you can show that this is an approximate solution to the original problem. And then what one does is that you can use this and the properties like equicontinuity. I'll explain what it is. Total boundedness, to conclude that there is a subsequence which converges. You cannot say that this sequence is a convergent sequence. In fact, there is a subsequence which converges, at least one subsequence. In fact, there could be more than one such convergent subsequence. Now you see that you can show that every one of these, the limit of every one of this is going to be a solution of the differential equation satisfying the same initial condition. Therefore, what you have, depending on how many different subsequences are there, each convergent subsequences are there, you will get corresponding solutions. Okay, so you see that a sort of non-uniqueness is built into the system. Now I will go systematically explaining this out. So the strategy is to approximate f by polynomials and then work on this strategy. Instead of considering this initial value problem, you consider this initial value problem, and then you get the solution for this. You can apply the existence and uniqueness theorem, get a sequence, you can show that it is equicontinuous, it is totally bounded, and then just use the sort of Arcelà-Ascoli theorem to conclude that it is a convergent subsequence. So let me just write down all the background results that are required to support this. The important point is that you are likely to lose uniqueness. You cannot guarantee uniqueness here. Okay, so let me just start with a lemma. I am not going to prove it. This is in analysis. We will be using it. So you can refer to any book on analysis. If f of xy is continuous in the region R, then there exists a polynomial pxy such that pxy modulus of pxy minus f of xy is less than or equal to epsilon for any epsilon given. Okay, did I not write epsilon? There exists a polynomial. Okay. Given epsilon positive. Given epsilon positive, there exists a polynomial pxy such that pxy mod pxy less than this. You can even choose the polynomial such that pxy is bounded by f of xy. This is a result due to isomers. See, what you are doing is you are approximating continuous function by a polynomial. The advantage is this: polynomials are very nice functions, they are analytic, therefore they are differentiable, derivative of any order exists, etc., etc. Therefore, you see that it's quite easy to see that they satisfy the Lipschitz condition. Okay, so this is one of the theorems that we are going to use. Now the next result that I am not going to prove this. So next concept that I am going to use is this. We introduce the concept of key continuity. Definition. A set of functions S is said to be equicontinuous over an interval compact interval AB if given epsilon positive, there exists delta positive such that if x1, x2 belong to AB and mod x1 minus x2 is less than delta, then f of x1 minus f of x2 is less than epsilon for every f belonging to S. What do we have? You see that you have a collection of functions now. Okay. Now in some sense what you are saying is that all these functions are continuous at the same rate. That is, given epsilon, there exists a delta such that for mod x1 minus x2 less than delta, yeah, please, yes, did you say something? Yeah. Ah, tell me. Yeah. Sorry, I don't understand your question. Yeah. 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 I will be using this to prove the theorem. Hmm. Yeah, exactly. Yes. That's yeah. That's a more generalized form of it. But this is something that we are going to use in a form in which we are using it. Because Stone-Weierstrass theorem, if you want to bring in, you will have to use, more sophisticated terminology, etc. Yeah. So I am not going to prove this theorem either here. Yes. You can look into books on analysis, and I think this is discussed in Rudin. Yeah, yeah. For compact set space, it proves it. But I don't know whether which book discusses the proof of this in the locally compact situation. Okay. Okay. Right. Okay. Right. So shall I continue? Okay. Right. So what you have is this. See, you have a collection of functions. Now, the term itself tells that it is continuous, and the continuity is at the same rate for all the functions in this collection. That is why you have for every f belonging to S. Now, let us look at what exactly is the consequence of possible consequence of this. I will explain it soon. Now we will, so this is the concept. Now let us go to the second lemma which we are going to use. This is the Arzel's theorem. An infinite set S of functions uniformly bounded and equicontinuous over a compact interval over a AB contains a sequence, a subsequence converging uniformly Okay, this is the theorem which says if you have the following conditions, you have the infinite set of functions defined on the compact interval AB, and we assume that they are uniformly bounded on the interval and equicontinuous. These are the two conditions that you impose. Then it contains a subsequence converging uniformly over AB. Okay, let us look at the following situation. Try to understand this result. What you have is this. Let me just let us take the interval AB, compact interval AB. Now you see that the graph of these functions is spread over this particular region. We are assuming the entire class of functions is uniformly bounded. So let me take, suppose this is a function, then you see that the statement that it is uniformly bounded means there exists an m and minus m positive, such that the graph of this function, all these functions are going to lie in this. Now the additional condition that you have is that it is equicontinuous. I will come to that. Before that, let us try to look at possible set of points that it fixes on a vertical line. How do you look at the convergence of these functions? If you want to study the convergence of a sequence of functions, then what you do? You look at whether it is pointwise convergent. Okay, so pointwise, what is happening here? So you take a point, say x0, and at x0, what you have for each function, it sets up a set of points. What do you know about these points? What we know about this point is that it is a bounded set. Okay, and in fact, it's an infinite set of points in a compact interval, because you see what is happening is there is the corresponding values here. So you have an interval say from minus m to plus m, and all these values are bounded by minus m and plus 1. So what is the consequence of that? Immediately you can conclude that it has a limit point. Okay, or you can go to the extent of saying that there exists a convergent subsequence of these points. Okay, right? But you cannot say that there is only one convergent subsequence. Okay, just from these conditions you cannot conclude that there is only one convergent subsequence. There may be many convergent subsequences for this set of points. Now you see that you are taking the whole interval. For each point you are doing something like this. Now what happens? Because of the condition that the functions are equicontinuous, as we have defined here, you see that the limit points patch up to give you a sort of continuous function. But again, the problem is that these limit points or the convergent subsequences would converge to a function, and now because of equicontinuity you can show that it's a continuous function. Okay, so this is the importance of this concept equicontinuity in this context. And once you have that, you see that there are subsequences of this which give you, whose limit are continuous functions. Now what you do is, for each of these subsequence, you show that their limit would prove to be a solution of the initial value problem that we have started with. That's why you get non-uniqueness. So this is the extent to which you can go. You cannot assert that there is exactly one subsequence which converges in this case. In some cases it may be the situation, but in general there is likely to be more than one subsequence which converges, and each one of this will contribute, the limit of each one of this is going to be a solution of the initial value problem. So what is the strategy? So the strategy is very clear now. What is it? You approximate f by polynomials. Corresponding to each polynomial, there is a solution for the initial value problem, because the polynomials do satisfy Lipschitz condition. Therefore, there is a unique solution corresponding to each polynomial for the corresponding initial value problem with the same initial data. Fine. What about and in fact you see that the sort of functions that you get in that case would be the following. You have all satisfying the same initial data. Therefore, the set of functions that emerges corresponding to each one of these polynomial will be something like this. See, they satisfy the same initial condition. Suppose this is the point x0. Suppose this is the point x0, y0 in this region, and this is x0, 0. Then you see that the graph of these functions are all going to be passing through this point. So they are all satisfy the same initial data. So what one gets is that if you can prove equicontinuity, then you can immediately conclude that this sequence of functions have what is called convergent subsequence. And then, as we have proved in the case of, say, existence and uniqueness theorem, you prove that each one of them will lead to a solution of the initial value problem, and that solution will satisfy obviously the initial condition. Okay, so it will be a solution of the initial value problem. Okay, right. Okay, so this is the strategy. You approximate with, you take make use of Weierstrass approximation theorem, get hold of the existence of such polynomials, and then write down the corresponding initial value problems, solve them, get the sequence of functions. You prove that it is equicontinuous and of course uniformly bounded. Then you can apply this lemma, and from which you will see that it has a subsequence converging uniformly over the interval. So there may be, the point is that there may be more than one such subsequence. Okay. So let us proceed to write down the theorem now. The statement of the theorem. So the statement of the theorem is that assume only continuity, nothing more than that. So we assume that you have the equation y derivative equal to f of xy. Now the initial data is yx0 equal to y0. Now we assume that f is continuous on the interval, on the region or even the interval AB would do, it doesn't matter. where h of course you take as minimum of you start with some interval AB, some rectangle S as we have introduced earlier with AB, and then you get your H determined, and after you get the H, then you consider only on this rectangle. You assume it is continuous on this rectangle, closed rectangle. Then there exists the solution of the initial value problem. On but this is where uniqueness cannot be assured. Okay, this is the problem. So let us look at the proof of this. I'll just outline the proof and you can fill in the details. Proof: apply lemma to get the sequence Fn. Polynomials such that where M is the bound for the function on the rectangle, and epsilon n is a sequence. Epsilon n is assumed to go to 0 as n tends to infinity. Also you can choose 1 by n. Now we observe that Pnxy is uniformly bounded. That is quite easy to prove. Now what we do is, see, we started with the F without loss of generality. Assume M is the common bound for Pn and so we assume Pnxy, modulus of Pnxy is less than or equal to M, and mod f of xy is less than or equal to M over this rectangle. That's the assumption that we make. Now the advantage that you have is that these are polynomials which satisfy the Lipschitz condition. R is this rectangle. In Y, that means for each x you have the condition. Therefore, now what you do is consider the IVPs. IVPs. The IVPs are the following: Yn y at x naught equal to y naught for all n. So this is a collection of initial value problems. Corresponding to each Pn, you have an initial value problem. Okay. So what do we have then? You can use the existence and uniqueness theorem. Okay. Before that, okay. So existence and uniqueness theorem applied to these IVPs assure the existence of a sequence of a solution for each of them on so that is guaranteed. Let us designate this by associated with Pn. Now we prove two things. See, then what you have is this. You have yn x minus yn x naught. This is less than or equal to that is quite easy to see. So it is in that rectangle you are going to have all these graphs of these functions contained. Okay. The second point is this. Yn x naught is actually y naught. Okay, so that is that. Now you see that yn is also okay. How do we get that? So you see that yn x2 minus yn x1 is equal to, see, we use mean value theorem, and what you get is yn derivative at some intermediate point psi x1. So using mean value theorem. But you see that, see, yn psi therefore you see that this is bounded by this and this is bounded by therefore what you get is that mod bounded by now what you do is given epsilon positive you can find a delta you choose as epsilon by m. Okay, if you do that then you see that yn x2 minus yn x1 is less than epsilon for mod x2 minus x1 less than delta. Okay, so we have yn x2 minus yn okay. So this delta does not depend on the particular x that you choose and also it does not depend on the particular n that you have. Right. So now we can apply the what is that, the main result, namely that is the second lemma that we have given, that it has a convergent subsequence. So let me okay. So hence by lemma 2 convergent subsequence now this is important, it has a convergent subsequence. Okay, it's not unique, not necessarily unique. So what we do is we haveynk which converges to some particular y without loss of generality. Okay, don't get confused here. Without loss of generality, we designate the subsequence also by yn. Okay, so without loss of generality, we designate this subsequence Now what we need to prove is that each such subsequence will give rise to a solution of the differential equation. We essentially what we want to prove, possibly the only step that you need in this connection is this. Okay, let this is equal to f. This we prove. I mean, how do we prove this? We can use the same technique. So use the arguments similar to the one in the existence and uniqueness theorem. This is what we do. Okay. And this is of course uniform. Okay. So what do we have? We have the following. We have yn x minus y naught is equal to this. We have proved in the case of, because once you are using Pn, this is guaranteed because we have already proved it for the functions, because these are the exact solutions that you are talking about associated with Pn. Okay, so we have already proved it in the existence and uniqueness theorem. Therefore, what you have is this. See, what we want to do is we want to estimate this. This is of course less than or equal to, you add and subtract etc. You will get this is less than or equal to integral x naught to, sorry, x naught to x, this is what you have. If n is greater than n, what we have is this mod Pn x y minus f of is less than or equal to epsilon. For mod x minus x naught, mod this we have. Therefore, you see that this is f of is less than or equal to epsilon n into h. Now what you do is you let epsilon n go to, sorry, n go to infinity. So let, then what you have, epsilon n goes to 0, and you can, as before, see, this is the crucial thing that you will have to prove. Okay, so let n tend to infinity, then using this limit, of course, this is the part which you have to prove, as in the other case, you will get the required result, namely So what you get is letting n tend to infinity, then what you have is that mod this is where you will have to use the theorem. Equal to 0. And that in turn tells you two things. One, of course, y is differentiable and the derivative is that is one thing. And you also have y x naught equal to 1. So the limit of the subsequence, the limit of the convergent subsequence will be a solution of the initial value problem. What one cannot guarantee is that there is only one such subsequence which converges. Okay, so this is built into the theory. That's why you see it's very fascinating how results in analysis are rather motivated by problems that you encounter in differential equation. In fact, differential equation has contributed quite a lot to various results in analysis. And ultimately what happens is those results go into our toolbox and we are keeping it as a tool. And we do not know where they really come from. Or see, this is one situation where you see that all these concept of equicontinuity and then what is called the Arzel's theorem, all these things come into play. Okay, so that completes the proof of this theorem. So we see that let me just put it down. We can ensure, we cannot ensure there is only one subsequence converges. Each convergent subsequence gives rise to a solution for and this is a non-uniqueness. Okay, so that proves this theorem. So we have seen that if you have the existence, the Lipschitz condition assumed, then you can prove that there exists a unique solution, and we have seen the role that the fundamental inequality plays in getting that out. One more thing that you should observe is that we have proceeded in a systematic way, namely that with the assumption that f satisfies a Lipschitz condition also along with the continuity, we could prove the existence and uniqueness theorem. Now, how to approach the general problem? Suppose you are to knock out that condition of Lipschitz continuity. Suppose you are to knock out that. How do you manage it? This is the problem. There you see Weierstrass approximation theorem just comes into play, and it becomes very useful. You can approximate the continuous functions on compact sets by polynomials, and each polynomial, the polynomial approximation has the advantage that they are all smooth functions. Okay, so this is a polynomial for two variables, not single variable. Okay, right. Okay, I think I think it is almost an hour. What I want to take up further is this, that the solutions depend on the initial data. Okay, each solution will depend on the initial data. Now you have seen the general problem. This is the domain D, and if you have F defined here, so it gives a sort of field of directions. So what you have is, this is what F defines. And what you have is, from the point from x0, y0, what we have proved is only a local existence theorem. And then you see that you have a solution with the property that whose graph has the property that its tangent to the graph coincides with the whatever field is prescribed there. So they become tangent field. This is what. So you see that if you change the initial data, there is going to be another curve, and there are a lot of curves of this kind that you have. Through each point there is a sort of solution that you have. Right now we have proved it locally. Locally means in the neighborhood of the point x0, not globally. Now we will ask this question, we will take up this question soon. Yeah. So what you have, one observation that you make is this. Okay, if you assume F to be Lipschitz, then through x0, y0 there passes only one and only one solution for the problem. There is uniqueness. Now, is it possible that two such integral curves, now these are called integral curves, okay, is it possible that two such integral curves would intersect? This is one question that you have to ask. But before that, I think we'll have to talk about the maximal interval on which the solution is defined. But until that I postpone it, but still let me just tell you what happens. So if you take this point of intersection as an initial data, then what this says is that in some neighborhood of the corresponding x0, there are two solutions for the initial value problem, which is ruled out once F is assumed to be Lipschitz in the neighborhood of that. Okay, therefore what happens? It leads to a contradiction. Therefore, you cannot have two integral curves, intersecting at any point, and that's one of the things that is built into this. All this comes from the existence and uniqueness theorem. Once F is Lipschitz, now you see that these integral curves are separate. Okay, right. So I think let me just stop here, and then maybe after say some 15 minutes I will come back, and then we will look at solutions containing parameters. Thank you very much. See, what I propose to do is this. I will start with another frame now. So you will have to rejoin. I am going to quit this, and then maybe I'll set up another frame, so that it will be another talk in the series, because this is just to avoid the inconvenience of editing it later, because otherwise if I leave it open like this, there is going to be sort of blank space in the talk, and which we have to edit and then remove. So I want to avoid that. So what I do is, right now I will quit this frame and then reset another frame. Okay, thank you very much.